Our next speaker for the session is Pedro Bahia. So Pedro will be speaking about some fuel samples. Which microphone do you want?
Hello. Okay. So, hello. It is already introduced. My name is Pedro Bahia, and I will present a work that I developed along with the group of research of the Georgia Porcaro and GF&PH, and guided by my advisor in Brazil, Maria Elizabeth Machado. And the work that I will present today is titled Quantification of Heterocyclic Aromatic Compounds in Unfractionated and Fractionated Fuel Samples by GC GC-ToFMS. So, first of all, we need to understand a little bit of the NSO heterocyclic characteristics. And the main characteristics of these compounds are the high resistance to degradation, the accumulation in the environment, but especially for the fuels that we are analyzing, is that these compounds are commonly found in fuels. And we have here on the side some representatives of each classes. And for the sulfur compounds, we have the DBT and the 4 and 6 DMDBT. They are considered recalcitrants, so there is these compounds offers a resistance to degradation. And as representative of the oxygen compounds and the nitrogen compounds, we have the carbazole and the dibenzofuran, that these compounds can provide the formation of gun in the motor engines. So, after that, the next step is to determine these compounds in the samples. So the most applied analytical methodology for their determination is the open column chromatography, and it's a pre-fractionation step. It's applied to the collection of the aromatic fraction, and usually it's applied the SARA method for that. And it's collected in the aromatic fraction all these compounds. So after the SARA method, the next step is another fractionation to collect these compounds separately. So first of all, for the sulfur compounds, they are collected using the palladium-2 complex stationary phase. For the nitrogen compounds, they are collected in 2 fractions, and the neutral compounds and the basic nitrogen compounds, and for that is used the silic acid column or the ion exchange chromatography. And the oxygen compounds, they are usually already collected in the aromatic fraction. So, to perform all of these methodology, we need too much of organic solvents and a big amount of sample, but especially there is too much steps in this procedure, which can reduce the recoveries that we obtain when we perform these kind of methodologies. So in this case, it appears the HPLC in preparative mode, and this technique can provide the reduction in the mistakes due to the reduction in the manipulation, but also, most important, the increase in the efficiency of the fractionation comparing to the results that it's already reported for these samples applying the open column chromatography. So, after the collection of the fractions, the next step is to analyze these fractions, and usually it's applied the GCMS for that. However, this technique has some limitations, and is regarding to the incomplete separation of these compounds related to the several numbers of structural isomers inside of these classes, but which can provide the formation of coelution events, but also it happens coelution events with the interferences that is present in the matrice, in the fuels, due to the high complexity of these samples. So, The GC GC-ToFMS appears in this scenario with all the advantages that we already know, but the most important to reduce the sample preparation, because the GC GC-ToFMS can be applied to the determination of this class, removing the necessity of another fractionation step for each class. And when we come to the literature, we will be able to see that the determination of the NSO heterocyclic compounds, they are usually qualitative analyses. The classes are determined separately, and there is a lack in the availability of the analytical standards, so which can limitate the quantification of these compounds in this kind of samples. So, the objective of this work is to apply GC GC-ToFMS for the first time for the simultaneous determination and quantification of the NSO heterocyclic and fuel samples before and after fractionation by HPLC. Initiating the experimental part, the first step was the preparation of the individual analytical standards, and for that we had available 20 standards of each class, the sulfur and the nitrogen compounds, and the oxygen aromatic compounds we had 13 standards. Here we have some representatives of each classes, of each compound that we analyzed in this study. In total we had 53 standards, plus 4 internal standards, 1 or 2 of each class, and we did a mix. We prepare a mix in a concentration for the further experiments. After that, we did the collection of the samples, and I brought from Brazil 4 samples of fuels, marine diesel, the diesel F500, and the diesel S10, and these numbers are related with the content of sulfur in these fuels, and also the gasoline. In Belgium, I collected the diesel B7 with 7% of biodiesel and the Euro 95. And here we have the photos of the fuels on the side. After that, the next step for the preparation was the HPLC fractionation. And for that, we first of all diluted the fuels with an hexane 10 times. And we applied the parameters of the HPLC for the fractionation that it's already developed and reported by the research group of Georgia. And after the collection of the aromatic fraction, that it's important, and to where are my analytes, we store for further experiments. And the next step was the diluted of these fuels with an hexane for 45 times. And we did that to directly inject these diluted fuels for further comparison between the fractionated and unfractionated fuels. So, after the sample preparation, we did the optimization of the chromatography method for the GC GC-ToFMS, and these are the parameters that we optimize, and here are also the column set that we use for the analysis. After that, we prepare the calibration curve, but we need to match the calibration curve with the samples because we are dealing with a complex matrice as full. So for that, we did a mixed extract preparation, and we apply a method already report for this kind of samples. And after obtaining the matrice extract, we prepare each level of concentration with this matrice. And we obtain, within the linear range test, good results of correlation and low limits of detection and quantification. Following for the validation, we follow the criteria pre-established by UPAC, and we evaluate the linearity of the calibration curve that we made, also the accuracy of the method, and for that we applied the addition and recovery tests in 3 concentration levels. After that, we did the precisions for interday and intraday in 2 different concentrations, and we also evaluate the selectivity of the method. After the optimization and the validation, we can finally analyze the samples by GC GC-ToFMS, the unfractionated and fractionated fuels. So, as first result, we have here the overall, the overview of the chromatogram that we obtain for the optimum conditions that we have, and we clearly see this, the use of the second dimension for the separation of the classes. So, here we have on yellow the compounds, the nitrogen compounds, and in red, the sulfur compounds, and we could see that with the application of the secondary dimension, we were able to separate the classes. And in this case, we will be able to optimize and determine 55 analytes out of 57. The other two, they are more heavier, so we were not be able to detect it in the experiments that we did. So, after we obtain the optimal conditions for the chromatography method, we need to evaluate the fractionation of the fuels. And for that, after obtaining each fraction, we analyze in GC GC-FID to see qualitatively if this separation was adequate, and we will be able to confirm. Following to the validation, we obtain a good linearity for the calibration curves that we made with values of P above of 0.05. For the precision test, we obtain values of relative standard deviation below of 20%. In the accuracy test, we obtain a range of recoveries of 56.6 to 103, and it's adequate for this kind of matrix that we were dealing. And for the selectivity, we were able, by the comparison of the matrix extract with that one enriched in a no concentration, that it was absent of our analytes. So, this was the first result, and now we're going to focus on the left that we have the samples for the marine diesel, and we have above the unfractionated ones and the fractionated ones, and we were be able to see that for the light sulfur compounds, we can see an increase in the concentration, and since they're increasing the molecular weight, they're decreasing the concentration in the fractionated samples. On the other side, we have the other fuel samples, and here we can see that the gasoline highlighted with the highest concentrations, and for the light sulfur compounds, and this can be related with what is reported in Brazil for the National Agency of Petroleum, that report that the gasoline, the limit is 50 ppm of sulfur, so it can be related to that. We were be able to identify 17 sulfur compounds in the fuels that we were analyzing. For the nitrogen compounds, we obtained significant results for the unfractionated fuels. Only the indole was the compound that we obtained good results for after the fractionation. But here we can see the same standard behavior that the marine diesel and the diesel S500 obtained the highest concentrations related to that compounds. Following to the oxygen compounds, we were able to identify 4 oxygen compounds in the fuels, but the interesting here is that we are not be able to see a big difference between the unfractionated and fractionated samples, but also the presence of dibenzofuran, because this is one of the first works that analyze this kind of compounds in this kind of samples, but it's already reported in the literature works that find dibenzofuran in gas oil, that it's also a product of the petroleum refine. And here, to explore a little bit more of the efficiency of the separation of the GC-GC, we will be able to see here we have the marine diesel diluted above and below the aromatic fraction and the TIC. And if we extract the ion related to the C2DBT, we will be able to see that the fractionated really affected, and it's really significant, and we will be able to easily identify the compounds that we are looking for, but also it improve the separation in this kind of samples. I have another example, and I choose these ones because they were the heaviest fuels that we have, and we saw that in the results that we obtained, and we seen the same standard of behavior and how the fractionation affected this kind of samples. So, to interpret all this data that we obtained, we decided to apply the principal component analysis, And for that interpretation, we will be able to see for the loading graph that this compounds target in here was the one responsible to discriminate the samples. And here we have the samples 1 and 2 that's related to the marine diesel samples, and the 3 and 4 that it's the diesel S500 but unfractionated and fractionated samples. We will be able to see that they were discriminated and separated, so how significant was the fractionation for these kind of samples. In the other side, we have a big cluster with the others fuels, fractionated and unfractionated, that we have. Following to the interpretation of the nitrogen compounds, we will be able to see what we expect for this kind of samples. As I said, we use the results for the unfractionated samples, and we will be able to see that these samples were well separated, and especially we have a cluster with the samples 3 and 4, that the diesel S10 and the diesel B7, that it's presents similarity in the composition of the nitrogen compounds in it. And finally, for the oxygen compounds, we are not be able to take any significant interpretation from it, probably because of the lack of compounds that we find. So the variability obtained from this data was not be able to take any conclusion about it. So, as conclusion of this work, the proposed chromatography method was efficiency to the simultaneous determination of the most of the NSO tested. It's a more simple proposal that can be reproduced for the determination of these classes of compounds, such as fuels. The validation complied with UPAC criteria with low LEOD and LEOQ, and adequate results for the precision and also for the recovery test that we apply. And the fractionation of the fuels by HPLC facilitate the identification and the quantification of the target analytes compared to the diluted fuel samples, especially for the sulphur class, and the PCA confirmed this information. So, I want to thank, first of all, to both groups of research that I was in, and I want to thank all my colleagues from the lab, everyone that helped me to build this beautiful work that I'm presenting now. I want to thank all the financial support that I received from Brazilian agency, and also to be here today. My university and the University of Liège that allow me to develop this work, and the workshop to give me the opportunity to speak here for all of you guys. So thank you so much. Obrigado.